to talk about the optical properties in the chapter 8. Well, we have covered the reflectance and the refraction, reflection, and absorption a little bit in the free electron model, but here I'm going to make a brief review of what we have done last time. The refraction, the R is the velocity ratio of the material and the light velocity, and that is going to be dielectric constant related, and permeability. Where is it? Mu r, and this is the permeability is always close to 1 in the optical range. So the refraction is very much related to, index of refraction is related to the dielectric constant of the materials. And absorption happens, then we have a complex refractive index, and then that is I gamma, and the gamma is the absorption index in this case. Absorption index. Okay, and since R square minus gamma square is related to the dielectric constant, we can say R square is, R square is going to be R mu R plus C square alpha square over 4 omega square, something like this. Okay. And also we have talked about the alpha, the absorption constant. Absorption constant. The variable which you can really measure in the material, that is related to the absorption index. In this way, gamma over lambda, okay? And gamma can be related to the alpha, something like that. And the complex absorption index, index of absorption, is going to be written as 2R gamma and C square over V complex velocity ratio, and then 4 pi sigma of omega C square. So the real values and the imaginary values has to independently equal in this equation. So R square minus gamma square is equal to dielectric constant, and 2r gamma can be related to the 4 pi sigma over omega c squared, as we have seen there. So you can have this equation. All right? That is the properties related to the optical properties that we have discussed so far. Now, in this chapter, what we are going to discuss is the reflection a little bit more. Optical reflection. Okay, this so far we have talked about the refraction. Now let's talk about the reflection, and then right after this we are going to talk about the absorption properties. All right, the reflection, if this is 0 and in this direction physically this is x, and then wave propagates towards the material. Okay, this is the material, and this is the incident wave, and this is going to be reflected wave, and this is a transmitted wave. Okay, so we are going to have 3 equations related to the to this situation. Okay, and can you get this? And if we talk about the plane waves, plane wave means round y, and round z is going to be 0. So if you draw x, y, z like this, okay, x is in this Cartesian coordinate, it means that in a wave front, we're going to have 2 components like in this electromagnetic wave, the light, okay? So one is the electric wave and the magnetic wave. Now if you set Fj xt is equal to e to the I omega r j star over c x minus t. Okay? Then epsilon y incident, we are going to write down the incident wave, electric wave, and it can be written as the amplitude and F1 xt. Okay? Now, since from Maxwell third equation, we know that if you change the magnetic field, then you're going to induce the electric field. Okay? So we can have a relationship between the electric field and magnetic field so that you have an equation like A over B is equal to R star over mu dielectric constant square root of this. Okay? If magnetic field of incident can be written as B F1 xt. Okay? So we can do the same thing for the reflected beam, and that is going to be y reflected minus A prime F1 minus x. The direction is the negative side, so we have to change the x, the sign, and for the magnetic wave, we can write down A prime R1 star mu naught square root and F1 minus x and t. Okay? And also we can write down the transmitted beam in the same fashion, like EY transmitted beam as a double prime now, and F2 x and t. We have a different values. Say here the dielectric constant is E1 and the gamma E1, and we have different material here, E2 and the gamma 2 absorption index, something like that. Then we are going to have different amplitude for the transmitted beam. And HG transmitted beam now is going to be, at the same token, it can be written as F2 x and t. Okay, now the conservation at x equal to 0 will give you conservation at x equal to 0, which means this conservation means nothing but the amplitude should be continuous. In other words, the incident minus reflected should be transmitted. Okay? So from this equation, you can get A minus A prime should be equal to the A double prime. And with the magnetic field, HZR should be equal to HZ transmitted. Okay? So from this conservation, you can have an equation like AR2, AR1, we don't have AR2. AR1 star plus A prime R1 star should be equal to the A double prime R2 star. Okay? Then the reflection, we have A prime A is going to be R2 star minus R1 star over R2 star plus R1 star. And that is R2I gamma 2 minus R1 plus I gamma 1 over R2 plus I gamma 2 plus R1 plus I gamma 1. Something like this, right? And reflection coefficient. Reflection coefficient. By definition, that is going to be the absolute value ratio of incident and reflected electromagnetic wave, and that is going to be R2 star minus R1 star and R2 star plus R1 star, right? And then if you manipulate the mathematics, then this reflection coefficient is going to be R2 minus R1 square, gamma 2 minus gamma 1 square over R2 plus R1 square plus gamma 2 plus gamma 1 square, something like this. Looks complicated, but in real practice, we don't have to use this whole complicated equation all the time. For example, if you have no absorption materials and vacuum. In other words, we have vacuum and this material is without any absorption, like a glass or something, okay? In this situation, the reflection coefficient is going to be, and R1 is equal to 1, so that the reflection coefficient here is simplified, simply R2 minus 1 square, R2 plus 1 square, something like this, all right? And another common case where we have vacuum, but the material shows the absorption index. Material medium has the R2 gamma 2 and alpha is going to be greater than 0, which means the material really absorbs some of the light. In this case, since in a vacuum, okay, in a vacuum, R1 is equal to 0. I'm sorry. R1 is equal to 1. R1 is equal to 1, but gamma 1 is equal to 0. Right? Then R now is going to be R2 minus 1 square plus gamma 2 square over R2 plus 1 square plus gamma 2 square. And that is going to be about 1. Okay? If the medium is a metal, which means the conductivity is very high. Then R is almost the same to the gamma, because R2 minus gamma square is going to be dielectric constant square, right? And the dielectric constant of the metal is almost a 0. It doesn't have any dielectric constant in there, in the metal case, because the conductivity is very high. So in this case, you're going to have a situation like R is equal to R2 minus 1 square gamma 2 square, and R2 plus 1 square plus gamma 2 square. And this is going to be approximately equal to the 2R2 plus 1 plus gamma R2 square, because gamma is equal to the R here, R2 square plus 2R2 plus 1 plus R2 square. All right? And this is equal to 2R2 square minus 2R2 plus 1, 2R2 square plus 2R2 plus 1, and then it is equal to 1 minus 4R2, 2R2 square plus 2R2 plus 1, something like this, right? And then it is equal to 1 minus 4 over 2R plus 2, and then it is equal to 2 minus 2 over R. And this is 2 over 2 pi sigma of omega. Right? This is the metal case. And if the conductivity is very high, reflective index is going to be 1. So that's why you're going to have all reflection in the metal case. Right? So we have metal texture. Everything is reflected on the metal surface, right? And the reason why is that the conductivity of the metal. Now, if you consider this reflectance, then you can work on the anti-reflection coating. This is very important, and the picture in the museum, and you have to put some anti-reflection coating on the coated glass on picture so that you can see the picture in every angle. Otherwise, on the surface of the glass, everything is reflected so that you cannot really see the picture. So anti-reflection coating is important in the display of the pictures. And the camera lens and especially industrially speaking, the solar cells, the anti-reflection coating is important. And the basic idea, it says here, we have an incident and the reflected beam here, and then this is the anti-reflection coating. Okay, and then this is a medium which has been deposited on top of the medium. The anti-reflection coating is going to be deposited on top of the medium in this fashion. And then here is a reflected beam at this interface, and then here is a transmitted beam, and which has to be transmitted at this boundaries, at this surface, and this T and R1 should be destructive. Okay, by manipulating the dielectric constant and the gamma values of this anti-reflection coating. And then basically we have to work on the thickness as well. And then we can calculate the proper thickness of this anti-reflection coating to make a perfect, the reflected beam goes to zero, make reflective wave to be zero, the amplitude. Okay, that has been shown in the textbook. So I'm going to give you the homework related on this. You may solve the problem. This is just a mathematical thing, not thing new on this. So I think it is not bad to, you can have a good idea or how we can control the anti-reflection coating to make the reflected beam equal to zero. Okay. So we have covered the refractive index refraction and the reflection. And then finally, we have to talk about the absorption phenomenon in a solid. Okay? The absorption. For the medium to absorb the light, three necessary conditions has to be met. Okay? First, there should be an electron to be excited by the light. All right? Okay? And then there should be an empty state and a medium to accommodate electron, excited electron. All right? And then finally, we have the enough energetic photon energy, of course. For the electron to be excited. So, if the material is intrinsic, perfect, single crystal, if the material is intrinsic and perfect single crystal, then there is a band gap here, and this is a conduction band, and this is the valence band. The band we have discussed in chapter 6, right? And then if there is a light h bar omega with energy h bar omega, this energy has to be big enough to make the electrons in the valence band to excite to the conduction band, and conduction band should be empty. Okay, so these three, then this light is going to be, we are going to say, observed in the material. If the electron energy, the light energy, photon energy is not bigger than the band gap, if h bar omega photon energy is less than band gap, then electron is not going to be excited to the conduction band, and the light is not going to be observed. If it is not going to be observed, then we say that is transparent. For example, the glass, the band gap is about 8 electron volt, and then the ordinary light cannot excite the electrons. The energy of the light is less than 8 electron volt, obviously, so that every light is going to be transmitted in the material. That is the glass, right? And semiconductor materials, typically, the electrons in the valence band can be excited with the light energies about 2 electron volts. That is sufficient because the band gap in a semiconductor is about, in silicon case, 1.9 or something, 1.12 electron volts, something like that. So the light can excite the electrons in the valence band to the conduction band, and by definition, if it is a semiconductor, the conduction band is half filled and less than half filled, right? So these three conditions can be met. And if the semiconductor has a shallow, the band gap energy is small, then every light can be observed. Observed here. In this principle, we can discuss about the absorption in a material which is not really perfect single crystal. So this is the typical absorption phenomenon in a semiconductor. We don't have to talk about the absorption phenomenon in a metal because everything is going to be reflected. We don't have to talk about the absorption phenomenon in an insulator because everything is going to be transparent, right? Every light is going to be transmitted. So if you want to talk about the absorption phenomenon in a solid, the solid should be a semiconductor. And then this is the absorption constant alpha. And we know that the alpha can be measured experimentally. And if this is lambda, the wavelength of the light, okay, so that the energy goes in this direction. This is the high energy of the light, and this is the low energy of the light. Then we have some absorption corresponding to 1, and then we have some slope here. And then we are going to have some absorption and something like this. Okay. I have to draw something like this. Okay. That is the absorption constant. And 1, 2, 3, 4, 5, and 6. We can distinguish the absorption phenomenon in a semiconductor. And this 1, 2, 3, 4, 5, 6. Okay. When band to band transition. And in this band to band transition, we have two things. One is a direct transition, and the other is indirect transition. And number two, is related to the transition between the band-to-band transition so if you have a small photon energy, then statistically it's going to decrease in this fashion, and then we can see that the band gap energy is going to be related on this number 2, somewhere in between these two, right? We cannot directly say with the absorption constant you cannot measure the band gap correctly, but band gap has to be lie in between this in the region 2, right? And 3 is the exciton absorption by the exciton, and this exciton is, if it is a conduction band, and there's a valence band, and then the light energy is not enough to overcome this band gap, but somehow the hole and the electron is going to be coupled by Coulombic force, just like this, and it stays there for a while, and then absorption happens to distinguish the hole and electrons, and then this has a binding energy related to the Coulombic force. Okay, so that is the absorption by the excitons. We call that couple as exciton. Okay, and number 4 is the impurity absorption. Number 4 is imperfection. Absorption, and it is related to the absorption inside this imperfection level. And if you have dissociation energies or ionization energy, it's just like this, then if some of the electrons are captured already in this impurity energy level, then this electron is going to be excited to the conduction band, and then accordingly we have absorption phenomenon. In this way, we can this material can meet the 3 necessary conditions for the absorption. It has electrons in the impurities. It has the empty conduction band nearby, and then we have enough energy for the light. So in this fashion, absorption happens, and we call this imperfection absorption. And then number 5 is the rest Strahlen absorption. We have seen that in omega versus k diagram, if you draw that the dispersion relations of the solid, it's just like this, and if you superimpose the optical absorption or optical energies on this same diagram, then the optical dispersion relations, optical energy is going to correspond to the y-axis, just close to the y-axis, just like this. And then here we are going to have a resonance, right? Resonance. That is the rest Strahlen absorption. And a big absorption happens in the solids on the way of the energies, light energies, just like that. And finally, number 6 is free carrier absorption. In free carrier absorption, it's nothing but if you have some electrons in the conduction band, okay? In a semiconductor, some of the free carriers will be sitting on the conduction band, and conduction band is not fully filled, right? In this case, the band, by definition of the band, it just says that you have a very narrow energy state where the gap is corresponding to delta E is about 10 to minus 12 electron volts. Almost we can regard this as a continuous energy levels. But in a conduction band, it is not fully filled. Some of the electrons will sitting half of the conduction band, and so if the light energy, even if the light energy is very small, these electrons can be excited to the next level, which is only 10 to the minus 12 away from this current band. So light can be observed, and that is going to be called free carrier absorption. And as you can see, if you have a considerable amount of free electrons, these electrons can observe the light in this continuously, even if the light energy is small. Okay. So next week on Monday, we are going to discuss the details of this absorption phenomenon. And finally, we're going to discuss about the application of this absorption phenomenon. Okay? Then I'll see you on next Monday. And have a nice weekend.